So now let's try the other approach of doing a voltage balancing instead.
Okay.
So we can undo the vacuum mode. Now you can see the regular chamber's pressure is right now 2 to 10 to the power of minus 2. Mm-hmm. So it's like 100 times less than 2 Pascal. So that's what we call normal vacuum in chamber. But this voltage balancing is nice. On this machine, it's actually a nice thing is that the help menu is very nice. If one click F1, one come into this guide and what shall I say, help. And they have a nice pictures. And this is what I want to show. Mm-hmm. So charging of the sample, how much it charges depends on the voltage you're running. Mm-hmm. And you can see in this graph here, so on the x-axis we have the voltage, and then we have the electron yield. And what is that? That means, is the sample becoming positively or negatively charged? I mean, are we ejecting more electrons than we shoot into it? Or is it the reverse?
Yeah.
And then we can see that curve has 2 equilibrium points that with the electron yield exactly 1. Mm. So that means if we shoot 1 electron in, 1 electron will go out also. And that means the sample will not charge out if we find that the voltage point. Mm-hmm. So, how do we find that voltage point? You can see in the table here is some kind of estimates. So we are running paper, here it says 2.65. Mm-hmm. I think I did this paper for a long time ago, and I think for this particular paper, I mean, there are many different types of paper, and for this particular filter paper, I think it's below 2, it's 1.8 or something like that, where we actually see this. So if you matches that equilibrium point of the material, you could actually monitoring it straight on in high vacuum. Okay. The drawback, of course, is if your material contains more than one material. Mm. You cannot have 2 voltages at the same time, right? No. So that's the drawback. It must be a simple single type material. Right. So let's check out that.
We need to decontaminate the chamber now, since we've opened it.
Yeah, we can show the plasma cleaner. It can be nice to do that. Mm. And this plasma cleaner is actually is a nice little hack that I have invented. I can show you that when I get online here. All right, the pressure is back. The system is back online. So now we have just removed the aperture because we don't need that if you don't do the low vacuum mode. So now we have a bigger view field. And let's start, I think let's start by 5 kilovolt actually, so we can see how it looks like when it is charging. So we come back to that kind of position. So here we're back in the nice charging case of our paper. And we want to go back to that place where we have the silver paint. Here it is. So this is the silver paint. And we are running at 5 kV. And let's go out here. This is view field 1 millimeter. So here we can see where the silver paint is. Perhaps we can have an even bigger view field, 2 millimeter. Now we see the paint in the top right corner that removes all charges, and we see the fibers that is not conducting. So they charge up a lot there. And you see they become white.
Yeah.
So remember that yield curve, if it became positive or negatively charged. So now let's drop the voltage. And in that guide, I think it said paper 2.65. So we can just let's try that. Now it looks a little bit different, right?
Yeah.
So we can take a quick images sort of over here. So you still see we have charging errors here. It's better than the 5 kV.
Yeah.
But still issues, and they are still white. Let's drop it to 2. And then you can go to 1.7 perhaps. So one problem that we have in a non-conducting sample is that when we are charging it up, even if we adjust the voltage, there will still be charges left there. I mean, they are, because since it's not conducting, they have a hard time escaping. And one way to get rid of charges is to, I mean, we could have go back to low vacuum, but that is, if we don't have the aperture, then that's like very tedious. And then one can actually start the plasma cleaner. So the plasma cleaner is a tool that is actually used for, what shall I say, remove contamination in the chamber, but it also removes all charges since it's a conducting plasma that we introduce. So, and you just need to run it for like 1 second. So here it says the contamination control. So usually you run this for like 5 minutes to clean up the chamber, but we just want to ignite the plasma to get rid of the charges. So we just start it, and that's the hole here. That is where the plasma unit is located. So now it will insert gas inside, air basically, and then it will start at high voltage supply there to ignite the plasma. And then we will see a bright white light soon here. Now you see it starts. And then it will increase the power also. So, and we just need to do like this, and now we can abort this, because now all the charges has been removed. The decontamination tool, if you want to use it to decontaminate the chamber, you just run it on that. It's a very, very straightforward. I don't think it needs more the training on that, so to say. But let's turn on the beam again, 1.7 volt, kilovolt. See, it looks different, right?
Yeah.
So we have removed a lot of excess charges that have been building up due to wrong voltage uses. And now we're starting to coming down that they're actually the correct voltage uses. So it still have charging issues. So let's drop this now to 0.3. And if I remember, I think 1.3 kilovolt is the sort of sweet point on this particular paper.
Okay.
So we will see what happens if we continue downwards, lower than that. Then it should actually start to become worse.
Mm-hmm.
You can notice the color changes.
Yeah.
Here it is white, gray, and then it starts to become dark. All right?
Mm-hmm.
So let's do 1 kilovolt also. Something like that, right? Some kind of demonstration of the voltage balancing, right? So in the guide it say 2.6 or something like that, right?
Mm-hmm.
But all cellulose papers are unique, and in this case you see the sweet point is between here 1.7, 1.3-ish range.
Mm-hmm. Yeah.
Then it starts to flip over from white to black.
Mm-hmm.
That means they have passed over that yield curve from going from too much charge to too little, reverse polarity basically.
Yeah.
So let's try to go out here now onto the paper. Let's try to take 1.5 perhaps here. That seems to be in the range there. Perhaps 1.6. Yeah. Now we're scanning very slow, so you see it's still charging in it.
Yeah.
So it's not easy. So how to solve that is, I mean, we can try. We have a beam intensity 10 also. I mean, it's actually quite high beam intensity.
Yeah.
So let's try to use the averaging function now, right?
Okay.
So we can grab the whole frame. All these images is 32 seconds, right?
Mm-hmm.
So let's try to make something at scan speed 1 that will be 32 seconds. That's like 90 frames.
Okay.
Let's try that. That means we scan as fast as possible.
Mm-hmm.
Like this. Take 190 frames and then sum that into one final data set. So we will have the same total acquisition time.
Mm-hmm.
And then we can compare that with the one that is scanned for 1 frame 30 seconds. Here you see, right?
There is a difference.
So now the images actually start becoming useful.
Mm.
So that is the non-conducting part.